Okay, at the Met Office we've been looking for more in-depth ways of evaluating our models. There are lots of processes that affect sea ice. You've got your radiative fluxes, air temperature and humidity driving a surface energy balance. You have your ocean heat flux driving a basal energy balance. Together those will interact with your internal sea ice energy fluxes to produce thickness and concentration fields, which integrated up give your ice extent and volume, with additional term for dynamic export of course. And of course your ice thickness and concentration will feed back on your surface energy balance through ice albedo and surface temperature. Although ice extent and volume are the only ones routinely evaluated at the moment, most of these terms, there do now exist some observations of radiative fluxes. For example, there are satellite estimates and indeed reanalysis estimates. There are, however, three terms in here which are still very difficult to observe, in particular the internal sea ice fluxes, the ocean heat flux and the basal energy balance. We don't really have large-scale observations of these. However, these can be estimated from devices called ice mass balance buoys. What are these? Slight misnomer, they don't float in water. They're collections of devices that are frozen into sea ice, basically. There have been over 100 of them deployed in the Arctic since the early 90s. Here there's a sort of composite of their tracks. They look a bit like this, often. You have acoustic sounders above and below the ice to show you the position of the ice surface and the ice base. You have thermistor strings within the ice that measure the temperature at 10 centimetre intervals. And together what they give you is something like this. This one deployed in 2012. A Hofmuller plot of the ice temperature, depth time, together with pictures of the ice base and the ice surface relative to a fixed reference point. Intuitively, this is potentially provides quite useful information. You could potentially estimate conductive fluxes within the ice from the temperature fields. You can estimate from the rate of change of position of the ice base or surface, the energy balance at the ice surface and the ice base, which you could theoretically combine with the conduction to get the energy arriving at the surface or the base, the second of which, of course, is called ocean heat flux. But there's a reason this isn't routinely done. While these tracks here, some of them look pretty dense in places, there is no way you can extrapolate between them to get any sort of map. Ice, of course, is incredibly heterogeneous. These tracks are point measurements. You can't extrapolate them over tens of metres, let alone kilometres. And this means that traditional methods of model evaluation won't work. You can't make these into any sort of map or integrate them into any sort of area total. Instead, I use a slightly different approach. Identify the two regions in the Arctic that are particularly densely sampled, the Beaufort Sea and the North Pole. And what we do, for each month of the year, we look at all the buoys for which a track exists entirely within these regions. We estimate the flux that we're interested in, and we collect together all those fluxes for that month, for that region, into a distribution. And then, for whatever model we're interested in, we look at all the grid cells in that region for that month, look at the grid cell mean flux for that month, divide out the ice area so that we don't get the open water estimates, and we compare qualitatively our distributions. We're still not completely comparing like with like in this manner. There are two particular problems. The ice mass balance buoys give you a Lagrangian perspective. You can see the blue line here. They float across different grid cells, whereas the grid cells in the model stay in one place and the ice moves underneath them. This is potentially a problem in areas where you have a large gradient in what you're interested in aligned with the ice motion. Also, potential problems with sampling. An ice mass balance buoy is pretty expensive to deploy, and as mentioned before, they don't float. So if you're a scientist out in the Arctic deploying one, you're not going to deploy it in thin ice that looks like it's going to melt out at the first whiff of a positive Arctic dipole. Instead, you want to deploy it in ice that looks like it's going to last. And so this means that the thinner ice categories in the model will not really be sampled by the ice mass balance buoys. There was actually a study done in 2006 as to how representative the ice mass balance buoy measurements were over larger areas of the ice. And the authors found that for certain things, deploying the buoys in level ice did actually give a reasonable representation. But you just have to bear in mind of this potential bias, because it doesn't necessarily mean that they're representative in every single situation. So, how do we diagnose the fluxes? Starting off with topmelt. Well, again, we're looking for monthly means. You look at your surface elevation. Here's a particular buoy again. Points above 0 are in the snow, points below are in the ice. Of course, above the snow, it represents much less energy because snow is less dense. We use this formula, rate of change of surface elevation times density times latent heat. We use constant values for now for densities of ice and snow. Obviously, snow especially is actually really variable, but it doesn't matter that much because most of the contribution to these actually comes from the ice. How do you distinguish between elevation changes due to top melt and other things? At the moment, just by sign. If the surface goes down, it's top melting. If not, it's something else, probably snowfall. This isn't perfect. You can see, for example, in December 2012, the surface goes down. By this method, that will be assigned as top melt. That's nonsense. The surface temperature is about -20. Instead, it's probably wind drift of snow. This means in the winter months you do get small top melt fluxes which aren't real, but for the summer months, which is when we're interested in it, this does give realistic estimates of top melt fluxes. What about the conductive flux at the top of the ice? In models, this basically represents the conduction downwards from the surface into your top layer. It's quite hard to estimate something similar for the buoys because you generally have a sharp change of gradient near the surface associated with the switch from ice to snow. And in order to deal with this, just gives an example, a buoy in November 2000, you can see here, again, sharp change in gradient towards the top. What we do, we estimate the interface temperature between the ice and snow and adjust all the temperatures here upwards by a factor equal to the ratio between snow and ice conductivity before taking our linear fit, and how it works for another buoy. We use the top 50 centimetres of the ice or snow to take our fit. Sometimes this lies entirely in the snow, sometimes it's split between the two. For conductivity, we use a fairly common formula which depends on salinity and temperature. At the top of the ice, we estimate salinity as 1 ± 1 PSU. It's a general slight problem with these buoys that you don't know the salinity of the ice. It's less of a problem at the ice surface than at the ice base. Yes, speaking of which, the conductive flux at the bottom, also quite useful to know how much heat is being stored in the ice, and because that is what directly causes ice growth. It's a bit more difficult because gradients of the ice base are often quite a lot smaller because the salinities tend to be higher. It usually means that you have to use some sort of reference layer above which the flux must be taken. This demonstrates how this might work. You take your conductive flux fit across this layer between 40 and 70 centimetres above the base. That means that you have to take into account the sensible heat uptake of the bottom layer as well when calculating your heat balance in order to estimate the ocean heat flux at the base. Demonstrates again how this might apply to a buoy. You estimate your bottom conductive flux here, estimate the rate of change of the base and the rate of change of the temperature, subtract those all, that gives you the amount of energy arriving at the base of your ocean heat flux. Again, use the same formula for the conductivity, but at the bottom of the ice, salinities tend to be both higher and more variable. Use 4 ± 4. For the very base of the ice, even this may not be high enough, of which more later. There are a few problems with these methods we've come across. False bottom formation under ice is quite a well-documented phenomenon, and this apparently happens several times in the periods of operation, and what you tend to see is sudden changes in the bottom elevation which don't coincide with any obvious conduction upwards. And this tends to give you high negative ocean heat fluxes, which are very suspicious things because don't tend to see them. And whenever you see these appearing in the table, go to have a look at the buoy in question, and yes, indeed, sharp change in the bottom elevation, which is then reversed a month and a half later. So these points are just removed from the data set. The temperature data, the thermistors in the buoys, I swear they're sentient. They like to have fun with scientists trying to analyse them, and there are all sorts of funny values that creep in. Can jump up to 0 or minus 100 at a moment's notice. Obviously, for this particular case, you can still estimate what you want for this month. You just have to remove these dodgy values, and this is all being done subjectively. Using uniform salinities can be difficult. For this buoy, the ice base, the temperature gets quite high. Estimating salinity as 4 plus or minus 4 PSU means that you effectively get an infinite flux because the temperature actually goes above the melting point for that salinity. Problem is, of course, that the temperature field actually carries information about the salinity, which would be great to take into account. Anyway, so much about the fluxes. These are the models we're going to try to use them to evaluate. HAGEM2, member of CMIP5 ensemble. HAGEM3, model we've just finished developing, be part of CMIP6. The ice models, HAGEM2, fairly standard multi-category model. It has zero layer thermodynamics, which means the ice has no heat capacity. Surface temperature responds instantaneously to the fluxes. HAGEM3 uses a version of SICE. It's pretty similar, but we've got multi-layer thermodynamics now. Ice has a heat capacity. We've also got explicit representation of melt ponds. Both models are quite unusual in the surface exchanges calculated in the atmosphere. Ocean model has changed quite a bit. We now use NEMO. It's got a tripolar grid with no polar island, quite a lot higher resolution. Both models use the atmosphere model, which in the new model has changed quite a bit, new dynamical core. For various reasons, the experiments we're comparing are not completely the same. Historical run for HAGEM2, present day run for HAGEM3, offset by about 10 years. Why? Because that's what is available at this time. Hopefully that will be improved. Just a quick look at the sea ice simulations before we jump in. So HAGEM3 is in red, HAGEM2 is in black throughout. Compared to HADIS from the relevant time periods, you can see HAGEM2, the black line is very amplified compared to HADIS. HAGEM3 is less so, ice extent slightly high in the summer. Look at ice volume. This is compared to biomass, which of course, rather than being truth, is a representation of what truth is probably not too far from. Again, HAGEM3 is very amplified compared to biomass. HAGEM3 somewhat less so. Can restrict to the Arctic Ocean, just look at ice thickness. Again, HAGEM3 very amplified, more growth in winter, more melt in summer. HAGEM3 somewhat less so, the higher annual mean ice thickness. In the process of comparing it to some satellite data sets as well, but for now I've also compared it to an analysis of submarine data by Drew Rothrock about 10 years ago, which again agrees that the thickness cycle of HAGEM2 is pretty over-amplified. Also looked at the surface radiation. We can see, for example, the downward shortwave that both models are a bit higher than various satellite and reanalysis estimates in May. In situ studies suggest this might be overestimated. Upward shortwave, big difference between the models in June. Say HAGEM2 doesn't have enough upward shortwave in June. Too much is going into the surface, not the case for HAGEM3. And that means we've got quite a big anomaly in net shortwave in June for HAGEM2. It's quite an interesting thing to bear in mind when we look at topmelt fluxes. Long wave down, both models don't have high enough fluxes in the winter. This is quite a common model bias. It's probably related to not simulating mixed phase clouds properly. Yeah, so that's surface radiation. Now if we look at the internal ice fluxes and compare them to the ice mass balance buoy estimates. So what we've done, this is the North Pole region, just collected all the grid cells in that region, converted them to means over ice, and this is the distribution of fluxes that you get. In many months, pretty similar. In June, that's not the case. HagM2 has much higher fluxes than does HagM3, and the same is true in the Beaufort Sea region. This is fairly physically consistent with HagM2 having much more net shortwave in June than does HagM3. So, this is the situation. Let the ice mass balance buoys adjudicate. So, we add in our distribution of calculated topmelt fluxes from the buoys to this, and they come down fairly firmly on the side of HagM3. They appear on the surface inconsistent with HagM2. We have to think about the sampling bias. The ice mass balance buoys are probably not sampling the thinnest ice category of HagM2. Obviously, the thinnest category, lower albedo, might be more topmelt. Could this explain the difference? Probably not, because the fraction of ice in that category in HagM2 is very small, and the flux that would have to experience to explain this discrepancy is hundreds of watts per metre squared, which would cause it to melt out in a few days. So yes, HagM2 is inconsistent with these estimates in the absence of a model bias, and the same is true for the Beaufort Sea region. You can have a look at net shortwave anomalies compared to the satellite and reanalysis datasets over the same regions, and in general the anomalies agree in magnitude fairly closely with what we see in the differences between the distributions. So far so clear. What happens if we look at conduction? Well, first of all, top conductive flux appears fairly similar in the two models, perhaps a touch higher HagM3 in the winter, and the buoy estimates again appear fairly consistent with both. When we look at the bottom conductive flux, it's very different. Remember, HagM2 is zero layer, no heat capacity, so the top and the bottom conductive fluxes are the same. They don't look at, that's just the different scales. HagM3, the bottom conductive flux is much lower, and that is important because it means there's going to be much less ice growth. And again, the buoy estimates are a lot more consistent with HagM3 than they are with HagM2. This is the sort of situation we've got. Because heat is being stored in the ice in the winter, the gradient at the base is much less high, and so you get less ice growth. Yes. Thank you. Yes, so we have to bear in mind conduction is very strongly dependent on ice thickness, so we have to think, is the sampling bias coming into play here? In order to separate out the dependence of conduction on ice thickness and other conditions, just use a simple model. Basically, we linearise the surface flux dependence on surface temperature, set that equal to the conduction through the ice, solve for surface temperature and then surface flux, and we basically get that the conductive flux is equal to this elusive thing, A, over a function depending on effective thickness, which is a combination of ice and snow thickness. If you plot one against the two, you can then get an idea of what the atmospheric forcing is. This is basically something that tells you about the atmospheric forcing, particularly during winter. It tends to take high negative values when the atmosphere is cold, lower negative values when the atmosphere is mild. Just to illustrate some likely values, the Arctic climate has been found to be strongly bimodal in winter, with net long wave peaks at -40 when it's cold and 0 when it's mild. If you plug some back in the envelope values into this simple model, you would get values of the atmospheric forcing of between -200 and -100. So these are the sorts of values we're looking for. If we plot conduction against effective ice thickness, we can see that the two models have very different distributions, particularly for the bottom conductive flux, because HagM3 has heat storage. The HagM3 tends to show milder atmospheric conditions than does HagM2. The ice mass balance buoys again tend to be closer to HagM3 than HagM2, both in the Beaufort Sea and in the North Pole. You can see the buoy estimates have very varied atmospheric forcing. That is probably because of the lack of heat storage in the model. The points down here tend to occur when you have strong cooling in the ice, meaning that the actual thickness you're cooling is not as high as it would be in the model. You can modify this to take account of heat storage, and I'll just do this very quickly. Basically, you use, instead of effective ice thickness, a thickness scale factor that takes heat storage into account. and this results in much tighter distributions. And again, you can see that HAGM3 has much milder winter forcing, and this is consistent with downwelling long-wave anomalies when you again compare to satellite and reanalysis. I could talk about ocean heat flux, but I'd probably better stop there. Oh, okay, ocean heat flux. So this is a bit different. You see the error bars of the buoy estimates are somewhat higher. This is because this depends on the rate of change of the ice base, and this is really, really strongly dependent on salinity. You can see that, again, at first sight, the model distributions are quite similar. The ice mass balance buoys aren't radically different. There are perhaps a few very high points, but that's probably what you'd expect because the model grid cells are over a wide area and they will smear out the high values. It's been found by various studies that high ocean heat fluxes in the summer usually ultimately derive from solar heating, which of course happens where you have low ice fractions. So this suggests that looking at the relationship between ice fraction and ocean heat flux would be quite useful. And you can see in the models there's quite a strong relationship. With HAGM3 perhaps it rises rather more quickly as the ice fraction drops off. What you can do is plot the buoy estimates against the what Hadist thought the ice fraction value was in that grid cell. You don't sample low ice fractions because the buoys don't survive in those cells. But in general, again, this is inconsistent with the models because the distribution is much higher at those high ice fractions. And this may be a resolution-dependent thing. Or it may not be real at all because of the uncertainty in salinity. If these estimates were all at the lower end, then this might not be right. And again, we're using 4 plus or minus 4 PSU. Is that realistic at the ice base? Not sure. Would appreciate some feedback on that. Anyway, those are the conclusions, and I'll stop there. Thank you.
One question, did you try to backtrack your snow conductivity from the continuity of heat flux assumption of the ice-snow interface and make sure that in your AGM model you also have that same snow thermal conductivity?
So look at the actual gradients of the snow and ice.
Yeah,
and
gradient, you know where the ice conductivity is, you know where the gradient temperature are, so you can backtrack your conductivity of snow.
That's true, yes. No, I haven't done that yet. Yeah.
Because what I find is that for in-situ data like this is much higher. It can be 0.4, 0.5, and people in the GCM use 0.2.
Yes.
And so that could have a big impact on your comparison with the conductive fluxes.
Is that related to horizontal heat convergence? Because there was
some study like this.
Yeah.
In-situ measurement of snow conductivity, like from the continuity of heat flux assumption, is really high.
Yeah.
So I'm just like throwing it out there. Like maybe it's a good thing to check.
Sure. Yeah. That'd be interesting. Yeah.
Thank you. Your turn.